Okay, so now we get to talk about light in terms of a wave, specifically the characteristics of frequency and wavelength, and then what we can do with them to get to energy. All right, so light actually has quite a wide spectrum of different types of light that you can be dealing with. And some of the boundaries, which I'm going to talk about today and in the next lecture, are a little bit arbitrary, but technically this is how it goes. You have gamma rays, X-rays, ultraviolet rays, visible rays, infrared rays, microwave rays, and then you have radio wave rays, which basically go from high energy on the left to low energy on the right. And the visible region is actually a very small region within the within the light spectrum itself. The visible spectrum, roughly speaking, starts at 400 nanometers and goes up until about 800 nanometers. Some sources on the internet will actually say that this is more like 750 where it stops. I'm going up to 800 just to keep the numbers a little bit more even. But one thing that I want you to notice is the colors. On the left side, we have purple or violet color, and that's because we are next to the ultraviolet region. And kind of want you to notice that similarity. Where the violet ends is where the ultraviolet begins. And on the other hand, at the other end of the visible spectrum, we have the color red. And past the red, we have the infrared, right? So you kind of have this nice little ways of correlating what kind of light you have. Ultraviolet is higher energy light than visible, but visible is higher energy light than infrared. Okay, so what we're going to do is look at the visible light given here in terms of wavelength, specifically 400 nanometers, 467 nanometers, up to 800 nanometers. Okay, so we have the units here. What we're going to do is we're going to use the data given to calculate first the frequency of these values. And the frequency in terms of wavelength is given by the speed of light divided by the wavelength. So what you want to do is input the speed of light 2.998 times 10 to the 8 meters per second. What you would notice is that if you divide that by the wavelength, let's say the 400 nanometers wavelength, you're going to encounter a problem. The problem is that the units don't cancel each other out because they're not exactly the same. So what you need to do is change the nanometers of the wavelength into regular meters. And for every 1 meter you have, there are 10 to the 9 nanometers. Since you have nanometers on the bottom, you place them on the top on the next fraction. The meters go on the opposite end. And your nanometers cancel out. Your meters will also cancel out. And all you will have will be 1/second, which are the units of frequency. Now it's very important that in this type of calculations, you get into the habit of using parentheses around your exponential numbers. Meaning that in this type of calculation, what I would do is open parentheses, enter 2.998 times 10 to the 8, close parentheses, divide by 400, press enter, multiply by, open parentheses, 1 times 10 to the 9, close parentheses, press enter. And then that should give you the following value, 7.49 times 10 to the 14 inverse seconds or hertz. Okay, so I'm inputting the value right here, 7.49, and we're multiplying that by 10 to the 14 hertz. Okay, so that's the frequency of 400 nanometers. All right, we could do the same thing to calculate, let's say, the frequency at 601. We would divide the speed of light, 2.998 times 10 to the 8 meters per second, by 601 nanometers. We change the nanometers to meters using 10 to the 9 as a conversion. And we end up finding out that the frequency is now 4.99 times 10 to the 14. So we enter the value underneath 601 to correlate it. And if we do the same thing yet again with 800, we're going to find out that the actual frequency is 3.75 times 10 to the 14. You could also perform the same calculation for the remainder values, 467 nanometers, 534, 668, and 735. And you basically will find out is that all the values have a number times 10 to the 14, so that's actually kind of a constant along the visible region. But what's changing is the regular number in front of the exponential. And what you see is that as the wavelength increases from 400 to 800, the frequency is actually decreasing. There's an inverse relationship between frequency and wavelength. Alright, so just to remind you, 1/2 is the same thing as hertz. So keep that in mind for frequency. Okay, now we're going to go further. We're going to calculate the energy of every photon of light associated with these wavelengths and these frequencies. And as you can see, I already put in times 10 to the negative 19 joules, because that's going to be the constant exponent associated with each one of the energy values in the visible region. And here we have two choices. We can either get the energy per photon by using Planck's equation that utilizes the wavelength, or we could use Planck's equation that utilizes the frequency. This is kind of a matter of, preference more than anything else, but I'm going to use both to show you the calculation through and through. So I'm going to start with 400 nanometer wavelength to do the calculation. So I'm going to start with the first equation, hc over lambda, to get energy. Planck's constant is 6.626 times 10 to the negative 34 joules times second. That's not joules per second or joules, it's joules times second. And then we multiply that by the speed of light, 2.998 times 10 to the 8 meters per second. We divide it by the wavelength, which is 400 nanometers. And much like in the previous calculations, we want to change the nanometers to meters, right? So you will multiply this by 10 to the 9. The nanometers will cancel out. The meters will cancel out, and the seconds will cancel out, leaving you with only joules. Alright, so here, yet again, it's important that you use parentheses for the calculation. So open parentheses, enter 6.626 times 10 to the negative 34, close parentheses, times, open parentheses, 2.998 times 10 to the 8, close parentheses, press enter. Then divide by 400, press enter. Then open parentheses, multiply, open parentheses, enter 1 times 10 to the 9, close parentheses, and press enter. And you should find out that the energy is 4.97 times 10 to the negative 19 joules. So I'm going to input that there. Okay, now let's switch over to using frequency. I'm going to do that for the next value. So the 467 nanometers, instead of using the nanometers, I'm going to use the hertz, 6.42 times 10 to the 14. And here, all you need to do is multiply frequency by Planck's constant. So we have 6.626 times 10 to the negative 34 joules times second, multiplied by 6.42 times 10 to the 14 per second. So the seconds cancel out, you end up with joules. And like I said before, open parentheses, enter number, close parentheses. Multiply, open parentheses, enter number, close parentheses, press enter. And you should find out that this is 4.25 times 10 to the negative 19 joules, which is the next value. Continuing this type of calculations to complete the series will actually show you that as the wavelength increases, not only does the frequency go down, but so does the energy. And another way to put this is that energy and wavelength are inversely proportional to each other, much the same way that frequency and wavelength are inversely proportional. This also means that energy and frequency are directly proportional to each other. Alright, now one extra thing that I kind of want to show you, not that it's super duper important, but since we're talking about joules per photon, looking at the equation that I had here before, with the Boltzmann constant, 1.38 times 10 to the negative 23 joules per Kelvin, if you multiply this by room temperature, what we basically get is an overall thermal energy, which is 10 to the negative 21. And this energy is actually lower than the energy associated with visible light. In fact, this is roughly energy associated with infrared light, which is mainly the reason why, people use infrared goggles to look at night, because we're always emanating heat, but the thermal heat that we generate is barely in the infrared region of the spectrum. Alright, one last thing that we're going to do is calculate the energy per mole, specifically in kilojoules per mole. So I'm going to start, for this you actually have to have the energy per photon to begin with. If you don't have that, you first need to get energy per photon, and then you do the following. Now typically when we write joules, it's kind of understood that we really have joules divided by photon. We seldomly write photons in any of the actual problems, but for this particular setup, you kind of need to write it out explicitly. So we're going to start with the 4.97 times 10 to the 19 joules per photon. Since now we have one photon on the bottom, what we do is we multiply this by Avogadro's number worth of photons, which is equal to 1 mole of photons. That cancels out the photons. And then what you basically do is change the joules to kilojoules. You divide by 1,000 joules, multiply by 1 kilojoule, the joules cancel out, and all you have left over is kilojoules per mole. Here, definitely use parentheses, enter the number, close parentheses, times, open parentheses, enter Avogadro's number, close parentheses, press enter. Divide by 1,000, press enter. You should find out that the value is 299 kilojoules per mole. Performing similar calculations will show you that the rest of the visible spectrum goes down from about 299 or 300 kilojoules per mole down to about 150. So that's roughly what we're looking at. And these are the type of calculations that I will have you do in regards to this type of problems. But this is also something I want to expect you to do for the photoelectric effect. So make sure to apply this knowledge to the photoelectric effect, where you can go from many different units. And I'm going to come back to the photoelectric effect in the next lecture when we start looking at all the different units. Okay, this is where we stop now.